Welcome to meeting 13 of Cryptography Club. We're going to talk about some specific details about RSA decryption and finding the private key D. Here are the steps for decryption. First, we need to find the prime numbers p and q, because we are already given n, so we need to prime factorize it, because n equals p and q. And then we find phi n, which is p minus 1 times q minus 1. And then the next step is to know the public key E has two conditions. We should already know the public key E when we're decrypting RSA, because it is given to us in the public key. So we just need to confirm that it is reasonable. When we have the public key E, we need to see that if it's a whole number between 1 and phi n, and whether it is co-prime with phi n. If it meets those two criteria, then we can go to the next step, which is seeing the conditions for private key D. For private key D, it has to, when it is multiplied with E and divided by phi n, it has to have a remainder of 1. In other words, E times D equals K times phi n plus 1. K is basically the answer when you divide ed by phi n, and then 1 is the remainder, which we add to k times phi n. So this equation is basically this statement put into an equation. And then for encryption, we know that the ciphertext is m to the power of e divided by n's remainder. And then for decryption, the plaintext is c to the power of d divided by n's remainder. So that's what we're going to need to do for finding m. But for today, we're going to see how to find the private key D. So the question marks are just brackets and commas. I think it's because I accidentally used the Chinese keyboard, so it doesn't recognize it. Next, let's talk about black box versus white box testing. There are two types of testing for software. The black box testing considers the external behavior of the system. So if you test using black box testing, you give an input and then look at the output to see if it's the right one. This type of testing does not look at any of the internal things happening in the system. It is carried out by testers, so there can be lots of people testing it at the same time, and it's not very time consuming. It is the behavior testing of the software, so it tests the behavior of the software. The white box testing is testing the internal functioning of the system, so like the logic within the system. It is carried out by software developers, and it takes more time because everything needs to be considered thoroughly. So this one is the logic testing. Because there are a lot of code to be needed in Python, and we don't always have a lot of time to write the code, we can find some resources online, because chances are that something that we need to do with the code, someone else also needs to do the same thing. So here are a few resources where we can find code. We can go to Python third-party libraries. So for example, we can import different libraries into our code, like we can import time and import turtle or import math to help us give us different functions that we can use in our code. We can also use GitHub to find different pieces of code. And we can also use credible wiki sites because they are reviewed by many people. Wikipedia also has some pretty good code in it because it is used by a lot of people, so if it has some sort of mistake in it, then it would have been fixed already. Next, let's talk about the extended Euclidean algorithm. So this is very similar to Bézal's theorem that we talked about in the last meeting. it says that given two integers a and b, there must be integers x and y so that ax plus by equals the greatest common divisor of a and b. So in RSA, we can use this because ed divided by phi n has a remainder of 1. So ed equals k times phi n plus 1, which can be turned into ed minus k times phi n equals 1. And then we can see that the format of this equation is very similar to this one. So we can use the extended Euclidean algorithm. We can correspond e to a, d to x, k to negative y, phi n to b, and the greatest common divisor of a and b to 1. So after we do that, that means we can find an infinite number of solutions for d and k. And d is our private key, so that means that according to the extended Euclidean algorithm, there should be an infinite amount of values for our private key d. Also, k needs to be a positive value for ed minus k phi n equals 1 to be able to use the extended Euclidean algorithm. Because y equals negative k, so when y is negative, k is positive. This makes sense because ed and phi n are all positive in ed equals k times phi n plus 1. Because originally it said ed divided by phi n has a remainder of 1, so when ed and phi n are all positive, k should be positive as well, because k is the answer of the division. Here is the Python function for the extended Euclidean algorithm. This is the code that I took from Wikipedia. This is a black box function, so we don't need to look at what is happening inside the function. We just need to know what we put into the function and what we get out of it, because we can trust Wikipedia that it has been tested by a lot of different people, so it should be right. So when we run the function, the input, which is a and b, are the public key e and phi n, and output will give us x, y, and GCD. Because we're using RSA, x is the private key d, y is the same as negative k, and the GCD should always be 1, since e and phi n are coprimed, so their greatest common divisor is 1. So the output is old s, old t, and old r. So old s is x, old t is y, and old r is GCD. This function is really useful because it solves the Diophantine equation and finds the greatest common divisor at the same time. The Diophantine equation is used when there is like an algebra that we need to solve, but there are an infinite amount of solutions. So because we're using this function, we don't need to talk about the Diophantine equation anymore. So this function is really useful. There is also a general formula for the extended Euclidean algorithm. So after we use this function to find one set of solutions, like one set of x and y that is a solution for a and b, then we can use the general formula to find all other solutions. So all of the other x's can be found by using this x0 that we found from the function plus b divided by the GCD and then multiplied by t. Similarly, y is the equals y0 minus a divided by GCD times t. So after we found using the function one set of solutions, which is x0 and x and y0, then we can use them to find all the x's and all the y's. And then so x is the private key d, y is negative k, but negative k isn't really important in RSA, so we just need to note this. Also, a is the public key e, b is phi n. So when we're calculating, we put the public key e into a and phi n into b. And then the t is just a loop variable m. It can be any integer. It can be positive, negative, or 0. So because we want the private key d to be a positive integer, if we get a negative integer, then we can change the value of t to find a positive one that we can use. x0 and y0 is any set of solutions for the extended Euclidean algorithm. So if we run the function, any set of solutions that we get out of it can be used as x0 and y0. So we can use the general formula to find many values, theoretically infinite, for a private key d, but we need to choose one where d is bigger than 0. D is the value of x, and then pick any one of them where d is greater than 0. We don't need to worry about the value of y because it's just a part of the equation. Y is usually negative, but k is positive because y equals negative k. Next, let's look at the code. So here's the code. For our example, we're going to use n equals 3233 and the public key e is 17. Here, this was explained in the first slide of the PowerPoint. It was just the process of decryption using RSA. And then here are 2 links for more information. The extended Euclidean algorithm is in Chinese, but the Python code part still works. And then here is the function for the extended Euclidean algorithm. We put in a and b and then get old s, old t, and old r. A and b is e and phi n, and then old s is the private key d, old t is negative k, and old r should be 0. So when we run it, we will get these 3 values. And then here is a data block. This is where we put the data that we want to use. We put a data block so that we only need to edit this part when we have different kinds of data. So then we don't need to edit the code part. If we just edit this part, then there is less chances for the code to get messed up. So right now, because our example is n equals 3233, so p and q are the prime factorized numbers of 3233. And then phi is p minus 1 times q minus 1, which will be calculated by the computer. And then e is 17, which was given to us. After the data block, we run the function using e and phi. We get the 3 values, which are given to x, y, and r. And then we print x, y, and r, and we give the value of x to x0, y to y0, so that later we can use those 2 values to find other solutions. And then we define the variable to check if the x and y are good values, because e times x plus phi times y has to be 0. That was the condition. If it is, then we return true. If it's not, then we return false. If it returns false, then there was something gone wrong. But usually it should return true. And lastly, this part is where we find all the different values for x and y. So the loop variable is m. We're going to do m from -5 to 15. We're going to find different values of x and y. So during the first loop, m equals -5, and then we're going to do x0 plus phi times -5 and give that value to x. Similarly, do y0 minus e times -5 and give it to y. And then we print x and y a few spaces afterwards, and then an empty string to make it not change a line. And then we check the result by using this function we defined before. If it's true, then everything was successful and it will print true. Even if it's false, it still goes on to the next loop though. And then the next loop will be m equals -4. and the loop continues all the way till m equals 14, and then it stops. So let's run. The first line is x equals negative 367, y equals 2, and the GCD equals 1. So because the GCD equals 1, we know that this is right. This is the only one we used with the extended Euclidean algorithm function. So this is basically the only time we used the function. The other times were all from using the general formula. And then this is the first result from the loop. So x equals negative 15,967, y equals 87, and this is true. So that means this pair of numbers is a valid solution. And then, but because we want d, the private key, to be greater than 0, so we can't use all of these, because for these the x are all negative. So the first one that we can use is this line from when m equals 1. So when m equals 1, the x equals 2753, and then this can be used for our private key d. All of these other numbers can be used as well because they're all greater than 0. So we can just, when we're trying to find the private key d, use any of these values of x. Also, we can notice that the value of y turned into negative, and this also makes sense because k needs to be positive, and k is equal to negative y. So when y is negative, k becomes positive, and that is good. So for our code, we can choose any of the positive solutions for x and then use it as the private key d. Thank you for watching.